Memories are another important part of our digital systems. So we store memory using memory arrays, and these efficiently store large amounts of data. And here's a picture of a memory array here on the right, and we have an input or address that we want, n-bit address, and we either read or write data into that array. So these arrows, we can either write that data or we can read the data out from that array. And so this n-bit data value is read or written at each unique n-bit address. So with a 2-bit address would have 4 or 2 to the 2 unique addresses. With a 10-bit address would have 2 to the 10 or 1024 unique addresses. There are 3 common types of memory: DRAM, which is dynamic random access memory, SRAM, static random access memory, and ROM, or read-only memory. And we'll talk about each of those. So here's an example memory. It's really small, but the principles extend to larger sizes. So memory arrays are two-dimensional arrays of bit cells. And so here's the kind of highest level view of our memory array. We have a 2-bit address in this case and 3-bit data. And so with 2 address bits, we have 2 to the 2 possible unique addresses, or 4, right? Address 00, 01, 10, 11. And so we can store 3 bits of data at each address. So for example, at address 00, we have the bits 0, 1, 1 stored there. At the address 11 or address 3, we have the value 0, 1, 0 stored there. And so each of these bit cells, we'll dive into what those are, this abstract view of them right now. That bit cell stores a single bit. And again, we have n address bits and m data bits. And we can also refer to this as 2 to the n rows and m columns. And so this number of rows is the depth, or the number of words that we can hold in our memory array. And the width is the size of the word. So in this case, we have 3-bit. This width is 3 bits, so our word size is 3 bits. And so this array is a 2 to the n by m bit array, a memory array. So we have 2 to the n, 2 to the 2 by 3-bit, or 4 by 3-bit memory array. In other words, we can store a total of, so we have a 4 by 3-bit memory array. We can store 4 words. Our word size is 3. And so we can store a total of 12 bits of data. So for example, in this 2 to the 2 by 3-bit memory array, if we look at address 10, for example, we have the word 100 stored there. We have the word size is 3 bits, and the number of words, or the depth, is 4 in this case, because we have 2 address bits. Here's another memory array. We have 10 address bits. So we have 2 to the 10, or 1024 words stored in this array, and the word size is 32 bits. So we have 2 to the 10 bits and 32 bits per entry, right? Our word size is 32. So each of those rows contains 32 bits. The width of our array is 32. And we can store a total of 2 to the 10 by 32 bits, or 2 to the 10 by 2 to the 5 bits equals 2 to the 15 bits of data, or 32 kilobits of data. So let's dive into what's inside of a bit cell. So each bit cell can store a single bit, and each bit cell has a word line, which is essentially an enable line, so that when this bit cell is enabled, it allows what's stored in that, a 1 or a 0, out onto the bit line. And so we're going to focus on reading. Writing is similar, except what's on the bit line gets then stored into that bit cell. And so let's say, for example, we have on these cases on the left, we have the word line equal to 1, so that means those bit cells are enabled. If what's stored in that bit is a 0, then because of our word line being 1, that 0 can go out onto the bit line and makes the bit line 0. Similarly, if what's stored in there is a 1, well, as long as the word line is 1, that 1 goes out onto the bit line, and the bit line becomes 1. In contrast, if our word line is 0, that bit cell is not enabled, and so there's basically no connection. Right? When this word line is 0, it says, oh, no, not enabled, can't go out onto the bit line. That bit line is then high impedance. So now let's look at the entire memory array. We have word lines, which again are like an enable, and a single row in the memory array can be read or written at any given time. And this word line corresponds to a unique address. So if we look at how we build this, we have a decoder here on the left, and our address comes into the decoder. And whatever address it is, right, with 2 bits, we have one hot output on our decoder. So if the address is, for example, 0, 0, this word line 0 is high and allows the bits in that row to go onto the bit line. And the bit lines are connected to the data output. If, on the other hand, the address is, for example, 1, 0, well, now word line 2 is going to be high, but only, remember, decoders have a 1 hot output, only word line 2 is high, the rest are 0, right? So we get a 1 here on word line 2, the rest are 0. And so only the bit cells in that row are enabled to drive the bit line. And so we can read that data then out on our data output. So in this case, when the address is 1, 0, we read out the values 1, 0, 0 on our data lines. So let's talk about what's contained in those bit cells, and that is determined by what kind of memory we're using. So there are 2 types of overall memory: random access memory, or RAM, and ROM, or read-only memory. And the names RAM and ROM are actually historical. The most important part is that RAM is volatile and ROM is non-volatile. So volatile means for random access memory, RAM, when I turn off the power to that circuit, that memory is lost. So volatile means if the power is lost, so is what was stored there. Non-volatile, or ROMs, means that when I turn the power off, that memory is still stored there. So for example, my smartphone, I took a bunch of pictures on there, and it runs out of power, it turns off. My pictures are not all gone because what it's stored on is ROM instead of RAM. Okay, so again, RAM is volatile, means it loses its data when the power is off, but it's read and written quickly. So this is an advantage of using RAM over ROM. And our computer memory is RAM. So DRAM, when you talk about how much memory your computer has, that's DRAM. Historically, it was called random access memory because any data word was accessed as easily as any other. So this is in contrast to like a tape recorder where it's not random access. It's, if you're close to that part in the tape, then it's going to be fast. But if it's, 2 hours later on the tape, that one's going to be harder to access. RAM or random access meant any data address was as easy to access or as quick to access as any other. Read-only memory, or ROM, is again the defining feature is it is non-volatile, so it retains its power when it retains its data when the power is off. ROM is read quickly, but writing is sometimes impossible, or like on your, on your phone or your thumb drive, it's just slow. So flash memory and cameras, thumb drives, and digital cameras all use ROMs, so that when the power is lost, right, you take your thumb drive out of your computer, the data doesn't go away. Historically, it was called read-only memory because they used to be written in the factory, and this was done by burning fuses, and they could only be written once and not written again. So they were called read-only memory. But again, that's clearly not true anymore, right? The flash drive that I use, I can both read and write that. So ROM now refers to the key feature of being non-volatile, retains its data when the power is turned off.